And then, you know, we can damage our soil, we can cut down all of our trees. So this is what we're really trying to quantify. Okay? But if you look at this, you say, wow, how do we put numbers on this? How do I determine if this computer is more environmentally impactful than that computer? Based on all of these look kind of fuzzy, right? How do I put numbers on these things? And what I'm going to argue to you is that we can put numbers on these, and we should, and it can help us design better stuff. Okay? So life cycle analysis is the method by which you add up all the inputs and all the outputs for anything, and you try to turn them into what it does to our environment. Okay? And we often think about products, so that's computers and carpeting and desks and chairs and cars, but it also applies to processes, how you make things, and systems, where you put a bunch of stuff together. So this campus is a system. It's got lots of products in it, it's got processes, it's got people, it's a complex system. And we can measure systems too. Okay, so what's a carbon footprint? All of that to get to what's a carbon footprint. A carbon footprint, as you can see by all these strikeouts, is where we just take one of these things, and because people have been so focused on carbon, because we think this global warming issue is a big deal, that they say, let's not measure these, let's just measure the greenhouse gases and only look at climate change. So a carbon footprint is essentially a simplified version of a life cycle analysis. It's only looking at carbon. It tells you nothing about acid rain, nothing about chemicals in the soil that could cause you to get sick. It just focuses on carbon, which is a big enough problem in and of itself that we should be focusing on it. We need to look beyond the carbon, but what I'm going to talk about today is how we just look at the carbon, and you could think about how you extend that to look at all of these things. Okay? So that's what a carbon footprint is. So let's look at it at 3 scales. We can look at the whole city of Roanoke and say, how much carbon does this city, this system, output in a given year? And the reason we would want to do that is if we're concerned about dropping that number, if we want to drop it 80% by 2050, as engineers, we've got to design products and processes that can help the city do that. Cars that run more efficiently, systems that transport people by bus better, okay? Products that you can remanufacture and recycle rather than make from scratch again. But this is a little bit like your budget. If you say to yourself, I want to spend a little bit less money next year, it's a good idea to know how much money you're spending this year and where you're spending that money. Because if you just kind of guess, I think I'm spending a lot on food as opposed to clothes, you might be wrong. So the numbers make a big difference. And if you're trying to make a decision in a huge city of what things should we do, a lot of times the politicians are just kind of guessing, hey, let's put more bus lines in. Let's put solar panels up. Those things cost different amounts and they have different impacts. And what we want to know is which ones of those give us the best reduction for the least amount of money. And you can't figure that out unless you look at the whole system. So we're going to look at all the energy that comes into Roanoke in a given year. Almost all. We can't look at all of it. And we're going to look at all the CO2 emissions that go out. I've drawn a dotted line here because, like in physics or in a lot of science cases, we have to draw a boundary. And models, if you include everything, get so complicated and detailed that you never can finish them. And if they're too narrow, you don't get the right answer. So it's this balance of complicated enough so we get most of the energy in the emissions, but not so complicated that we can't really even finish it. So here's what we're going to do. We're going to take all the inputs for the city of Roanoke and all the outputs, and we're just going to look at this particular environmental impact. We could go back and look at these others and talk about them. It's not that they're not important. It's just that politically people have decided carbon's the one we need to go for first. There are lots of folks who would rather, you know, if you're a trout fisherman, you want to be looking at ecotoxicity in the water. Okay? If you're growing vegetables and you're a farmer, you might be worried about the soil being depleted. But in general, people have decided, another reason carbon's so important is because almost all the carbon, as I told you, is coming from burning stuff. That stuff that we're burning costs us money. So it's tied intimately to our economy. And for many of us that are on limited budgets, if we can reduce carbon here, the way we do that is reducing energy here, and that puts money back into our pockets. We burn less gallons of gas. We use less kilowatt hours of electricity. We burn less natural gas in our house. So it's not just an environmental issue. It's an economic issue as well. So here's what we do, and I've done this baseline for the city. I talked to City Council this week about it, in fact. We say we're going to look at the city limits, so we can look at a map and we say, okay, that's our boundary. We know where the city of Roanoke stops and the county starts and Vinton starts. So just the city. We're going to look at residential, commercial, and industrial activities, so we're not going to leave out one of these big sectors. We're going to look at electricity and natural gas, gasoline and diesel, and waste. We're leaving a few things out here, but we've decided that they're small and not a big deal, and it helps the calculation. So we're leaving out, for example, propane, or if you're using wood. Okay? And that means this analysis is a little bit off, but the fraction of people that heat their house with wood compared to all these others is so small, it would be in the noise of the analysis. So that's something, and it's hard to collect data. You'd have to survey everybody in the city and say, how much wood do you use? Whereas for electricity, we can go to the electric company and say, we just want that number. For every house in this map, give us the number, and they can do that. So we go to Appalachian Power and we ask for electricity. We go to Roanoke Gas and say, how much natural gas do people use? We go to the Virginia Department of Transportation and we say, how many miles do people travel on our roads? If you've ever ridden across those road strips, they're counting how many cars are going by on each road every year. Approximately, you can't account for every single mile, but you can get a pretty good number. And then if you know how efficient that car is, you can turn that into gallons of gas, right? If I have miles and miles per gallon, I can divide those and get gallons. That's what I want to know is gallons. Miles are interesting, but not as interesting as gallons. And then I use some software to do some estimates, and I can get all the greenhouse gases, so not just the carbon, the other things too. And I also can get something called EPA criteria air pollutants. These are other things which the EPA has decided are harmful for our health, and there are limits on these. Cities are supposed to stay below these limits for carbon monoxide, sulfur, nitrogen, VOCs, and particulates. So this software gives me both of those in one shot. So here's the results. This is 2008. 2009 and 10 don't look that much different. I had better graphs for these. This is energy use. So a third of the energy in the city is transportation, and about 20% each for residential, commercial, and industrial. So this is your house or apartment. This is a small business or a grocery store. This is Coca-Cola, Roanoke Steel, Norfolk Southern, the big industries. Okay? If we look at where this energy comes from, again, it's split. About a third of it is electricity, a third of it gasoline, less than a third natural gas, and a little bit of diesel. Okay? Now remember, I told you before that depending on what fuel you use, it has different amounts of carbon dioxide. So now I'm going to take these energy numbers and I'm going to turn those into carbon dioxide numbers just by multiplying by a factor. That says for every gallon of gas, how many pounds do I get out? For every kilowatt hour, how many pounds do I get out? And I get similar graphs. So here's emissions by sector. You see transportation goes down a little because gasoline is not as intensive as electricity. And here you see electricity almost doubles because it's got a lot of carbon in it per unit. A takeaway from this, if you're the city, is if I want to reduce my carbon emissions, where should I start? Things that attract electricity compared to recycling paper are better choices. I mean, lots of times we talk about recycling, and we should not omit that. But if you're going to spend money on something in the city, electricity is the place to start. So this guides your decision making. It also says that everybody's got to be involved. You can't just have residents do things. You can't just have commercial folks do things. You can't just have industrial folks do things. You've got to attack this at all levels, right? And without the data, you couldn't say this. You'll see when we look at other things, it'll look a lot different. This, a city is so many different things that it's not surprising that we have a little bit of everything going on. If this was Detroit, the industrial portion, well, Detroit's having trouble. If this were, if this were LA, the industrial, well, they're going to have a lot of transport. So depending on what city you pick, the pie shifts a little bit, right? And your city might really need to work on transportation. If you're way out in the suburbs, you may have a big residential footprint, okay? So if you're in Arlington, far enough out, and you've got really big houses, right? But not a lot of industry. Your residential may be the biggest chunk. So the question is, this can tell cities when they decide, how am I going to go about doing this, where to put their money and their effort. So it helps you make decisions. And that's one of the key things. And that's one of the reasons I decided to talk about carbon footprints, because I could have given you lots of technical details about some engineering product. But my general feeling is that environmental awareness is going way, way up, but environmental action is kind of stalled. So people know that there are more environmental problems now, but they're still not doing anything. We need people to do stuff. And this kind of analysis will help you decide if I'm going to do something. You don't want to decide to put new windows in your house and spend $5,000 and then the next year realize that your energy bill went down 0.2% because windows aren't the best choice compared to insulation, say. Okay, so if you're going to do action, you want data so that your action really makes a difference. And some of these things have bigger differences than others. This is the numbers, just to give you a sense. 6.3 billion kilowatt hours of electricity. I had to turn all of this into some energy unit. So we don't think about gallons of gas in terms of kilowatt hours, but you can make a unit conversion there. And it's 2.3 million tons of carbon dioxide in Roanoke in a given year. Okay? It's hard to get our heads around numbers like this. You just look at them and say, wow, that's big. Okay? So this may help. And if you have another way to, I try to come up with ways for people to get a sense of how big this really is and why we need to take action, not just say, oh, okay. So here's why it's important. That's a ton of carbon dioxide. It's a block of gas 26 feet on a side. So, twice as tall as this room, about that wide, and about, let's take this room and at least double it, maybe a little bit more, right? Just carbon dioxide. That's 1 ton. Here's a physical map of the city of Roanoke, right here. Okay, you can see Orange Avenue, 581. Let's start putting some tons in here. The average household in the U.S. emits about 21 tons a year. These aren't to scale. I don't have enough of them. But I've put about 1 household's worth up here now. If we really wanted to do this for that 2.3 million tons that the Roanoke emits every single year, it's 1,500 of these cubes on a side. So it's 7.5 miles. It's this area of the map filled with these 26-foot cubes. That's how much carbon dioxide we're emitting. Okay, and a typical house emits about 20 of these a year. So 20 of these rooms times twice the height. We don't see it because it's invisible, right? You don't see carbon dioxide coming out the back of your car. But every time you drive a gallon of gas, this is mass in, mass out. A gallon of gas weighs about 6 pounds. So every time you burn a gallon of gas, 6 pounds is being converted into energy, but that mass doesn't go away. It just changes state. So you have about 6 pounds of carbon coming out the back end. In fact, you have 20 pounds coming out because it combines with the oxygen. Right? It turns from carbon to CO2, so you actually get 20 pounds out of carbon for every gallon of gas you use. Okay, so this is Roanoke, 1,500 cubes by 1,500 cubes. This shows what Roanoke has done over the past few years. This is a good sign. Since 2005, the carbon numbers have gone down 2%, and they've gone down in these different sectors. The disappointing piece here is this number right here. This industrial minus 24%. If you took this out, this number would be a big positive number. This is most likely almost all due to the economic downturn. These are the big industries saying we're not going to make as much stuff because we don't have consumers to buy it. So a big part of this drop is the economy. And if the economy comes back like we're expecting it and we want it to do, we've got to deal with the fact that all of our reduction is on this industrial sector. So it's good news, bad news mix. At least we're going in this direction. If the economy comes back, the industrial people really need to work on keeping their emissions down. The other thing people often say is, well, the city government itself needs to start. It's not the citizens and the businesses. This little slice here is the entire municipal government of Roanoke. Police department, fire department, all of the municipal buildings, the courthouse, the city market, the Roanoke Civic Center. We added all the city stuff up. it's 2% of the whole thing, which means you could shut down the entire government and only save 2%. So what it tells you is it's the community that, I mean, the city's got to do something too, but it's not just the folks in government. It's everybody has to drop this number down because we're contributing 98% of the carbon and the city is contributing a smaller portion. The same thing happens when these are the criteria air pollutants, okay? They're all, the municipal piece is less than 2% for all of these things. These numbers are obviously much, much smaller. We're putting out a lot of carbon dioxide, a lot less nitrogen oxide, sulfur dioxide, carbon monoxide, okay? Before I move on to the other scales of this, here's some examples. I showed you those blocks of CO2. Anybody know anything about weatherization? I think you guys talk a little. Some of the community college have programs in weatherization. It's sealing your house up. It's insulating it well. It's putting high efficiency stuff in it. If you do that in a normal old house in Roanoke, you can save 40% of your energy. Okay? That's a huge savings in a house. If we want to get 10% reduction, we have to do this for about 10,000 residences in the city. So it's a big scale problem. Just to do 10% residential, we need that. How about CFLs, these curlicue lights? Huge energy savings. A 75-watt regular bulb can be reduced 75% roughly to 18 watts for less than $2. So this is a huge savings. Okay? If we want 10% reduction in emissions just from bulbs, we need 5 per household. We need to buy 200,000 CFLs. So this gives you a sense of how big of a scale this is. Let's go to automobiles. If you've got a bunch of money, maybe you want to go from a car that gets 20 miles per gallon to one that gets 35. So 15 mile per gallon increase. That's pretty good. We need 1,200 people to do that in the city of Roanoke to get 10% reduction. So this just gives you a sense that this is possible, but it's not easy. It's not just change a light bulb here or there. It's change 5 light bulbs in every single house in the entire city. And then you get 10% of the way. Okay, so let's do the same thing for campus. Let's take the whole campus. Let's look at all the energy that comes in. Let's look at all the energy that goes out. And let's do the same thing. Let's look at climate change. Okay, it's a little bit easier because we don't have as many buildings. We don't have to do the whole community, but we have a different set of constraints. Right? We use the campus boundaries now. We're going to include the buildings and the grounds, but this analysis doesn't include student and faculty transportation. So it doesn't account at all for you coming and going from here, okay? Because that's a hard number to get. VDOT could give us all the roads for Roanoke City. It'd be nice to add this number in because this is really part of what happens here. This is a commuter campus. So the number you see does not have this in because it's a really hard number to get. We could do a survey, and if we got most people that come to campus to tell us how many times they come per week, how many weeks they're in school, and how far they drive, and what the fuel economy is on their car, we could try to do that. But try doing that for 10,000 people. That's a hard analysis. So that's one of these simplifications we've made. So this isn't going to be a perfect analysis, but it's not bad. So we're going to look at these other things, though. We are going to count transportation fuels for vehicles on campus, right? Because those are controlled. There's an accountant somewhere that knows how many gallons of gas the maintenance guy is using. Okay? Instead of using some big fancy software, we can do this all in an Excel spreadsheet. This is really easy to do. So here's what the spreadsheet looks like. You can calculate, here's the numbers that you get from the utilities. Here's how much energy is used, natural gas, propane. Here's the intensity of those things, so I have to multiply this number by that. This says that electricity in Roanoke on this campus in 2010, every kilowatt hour required 1.7 pounds of CO2. So I can multiply this by that and get a total carbon footprint on this side. So electricity, natural gas, propane, here's gasoline, on-campus cars, not faculties and students, diesel, water. We take water for granted, but somebody's got to purify it and pump it here. Okay, that's one of the things that green engineering talks about. In the U.S., we purify all this water so we can drink it. And about 85% of that water we don't drink. We flush toilets, we wash cars, we run steel mills, we do all sorts of things. But it costs us something to get clean water. We've got to filter it, we've got to pump it. The Europeans do it much differently. Almost none of their flushing water, for example, is drinkable. Why use drinkable water if you're just going to flush it? Okay, because it costs you something. So that's water. You also get credit for recycling stuff. For every pound of paper you recycle, you're saving almost 4 pounds of CO2. Where's the aluminum number? It's even better. Every pound of aluminum is energy intensive. It's a metal. You got to melt it and cast it and mold it. Almost 10 pounds of CO2 saved for every pound of aluminum. So these are all credit numbers. So you get to subtract these from your total. Okay? So here's the total on campus, 6,400 tons annually. A lot less than 2.3 million for the whole city. But the question is, if you guys and your administration and the faculty wanted to do something different, where would you start? Probably with electricity. Electricity prices are going up, and electricity is the dominant piece here. If we added in student and faculty transportation, the gasoline piece would be a lot bigger wedge. We could estimate that. We could say 10,000 students traveling 10 miles with 25 miles per. We could do a decent estimate. But this says start with electricity. Okay, buy better lighting systems, buy computers that use less energy, turn out lights. Worry about all that before you worry about fixing your industrial heating boiler. Okay? And here's what's happened over time. It's going up and down. Okay, so the city you saw kind of slowly going down. This is changing. But you've got to ask more questions here. One of the things that's happened in 2010 is you added some space. In 2011, because of the building, which is which way? It's going to go up even more. And a lot of people say, well, we shouldn't be penalized because we added a whole new building. I mean, per square foot, maybe that's a really efficient building. So our energy use per square foot is going down. Why penalize us for getting bigger? We're growing. That's a good thing, right? The environment doesn't care how big the school is. The environment cares how many pounds of CO2 are out there, right? So this is a tricky argument. If you grow, you've got to grow even more efficiently than you don't grow because you've got to bring the number down even if you're getting bigger. This is the problem with vehicles, right? Every year the vehicles get a couple miles per gallon more efficient. But if we double the number of vehicle owners in China and Asia, 2% efficiency gains are not going to help us. Overall, we're going to use more gasoline and emit more carbon. This is the problem that people had in the 70s when they went to energy-efficient refrigerators. California gave away like 1,000 energy-efficient Energy Star refrigerators, much more efficient than everybody else had. And then they did some analysis, and they found out that these houses were using more electricity than they used before, and they couldn't figure it out. So they sent graduate students out to interview these people about the new refrigerators, and they said, yeah, we got them at the same temperature. They're great. They're really quiet. They keep the food cold, all that. And it's great because the old refrigerator is in the basement cooling the beer and the soda. So even though the new refrigerator was half as much energy, it was like they were using 1.5 refrigerators. So scale really makes a big difference. These new flat screen TVs are much more efficient per square inch of area, but when you start getting 50-inch screens, all of your savings are gobbled up by the size of the thing. So scale makes a big difference. And this is a problem that lots of companies have because they say, well, our emissions went down per dollar revenue, but they increased their revenue by a factor of 10. They had a great year. The environment doesn't care how much money you make. It cares how many pounds of stuff ends up in the river. More efficiently putting toxins into the river doesn't help us. So if you're growing like a university, you've got double problems, which is your energy bill, even if this new building is LEED certified and uses half the energy of everything else, it's still more energy unless you take away a building the same size and tear it down, which is typically not what happens. You can do this at your house or your apartment. So this is my house. It's like 2 miles from here. And this is one of my cars. So energy and emissions. So what am I going to do? I want to make the world a better place. Do I buy a new car? Do I put new windows in my house? Let's look at this again. I'm going to look at the same stuff. It looks a lot like the one we did here. I'm going to go to my bill, and I can get this data. I just pull my bills up, right? It's often online now. They collect it for you for a long time. I'm going to use an Excel spreadsheet. Here's the bill from last year, 2 years ago. Here's kilowatt hours. It tells me how many kilowatt hours in this month and how many over the last 12 months. So I just grab this number. Here's the gas. Here's how many therms I used. February 2000. This is a really old bill, 2001. Okay. And I can just stick them in. Here's gallons of gas. 8,900 miles, 3,600 miles, 22.3 miles per gallon, 17.5 tons. My house. What do I do? Well, I should probably start with electricity. I could buy a new natural gas water heater, but if I look at the water heater, the amount of natural gas it uses is not all of it, because we also have a natural gas dryer and a natural gas stove, so it's probably a third of this. So that's probably not the place to start. I mean, I need to look at, what I really need to look at, you could have another column here that says, how many dollars per ton, right? It turns out I could buy solar panels and reduce this electricity, but the dollars per ton for solar panels is still really, really high. The things I can do really quickly and really cheaply are like change every single light in the house to a fluorescent. That would, and we've almost done all of that. But it gives you a sense of what you can do. Okay? So these things answer questions for you. If you want to do something like this, you can go here and download both a PDF version of these spreadsheets for your house and an Excel version of it. So you can go and do this. Or you could do it for a company as a project. Or you could do it for one building on campus. Or, some campuses that are not commuter campuses will do dorm by dorm and have competitions. Okay, so it gives you some instructions on how to do it. This is the actual, if you go there, this is the actual thing you get. You can do it by hand. You can just write in the numbers here and you multiply these two columns and then add them up at the bottom. It's really easy to do. These numbers, we didn't talk about them, but these numbers come from science. You can measure what the output of CO2 is for every gallon you use. So that's a science number. Okay. So last point, and we're just about out of time. You can quantify environmental impacts, and if you want to make better decisions about any kind of product you're making, any kind of process you're running, or any kind of system you're involved with, you can quantify that. And if you don't quantify it, it's hard to make decisions. Okay, one way to do it is by this thing called life cycle analysis, which if you end up coming up to tech, you can take a whole semester long version of that. What you saw today was a really narrow version of that, just greenhouse gases, lots of assumptions to reduce the size of the analysis. Think about calculating all the inputs and outputs for the entire manufacturing of a car. The tires, the engine, the glass, the leather seats, everything. It's a big job. But if you don't do it, you're just kind of guessing as to how do I reduce my impact. And then if you apply this at the community level, at your church, at your campus, at your small business, or at your house, it can help you make decisions. Because we all have to make decisions about what we're going to do, right? And if we take our role, seriously about I want to reduce my impact on the earth, you have to decide every day what you're going to buy. So organic versus not organic. Take the bus versus ride the car. Turn up the thermostat in my house or not. These are all decisions. And if you don't do some kind of numbers around, if you don't quantify it, you're just kind of guessing. And a lot of decisions we make now, we just kind of guess. City government says, let's do this. It sounds great. So this allows you to use science and engineering to kind of make better decisions. Okay? So I'm happy to take questions about this, and I'm happy, if there aren't questions about this or after those questions, to take questions about green engineering at Virginia Tech. So I'll open it up to any questions people have.
Any questions for Dr. McGinnis?
Has anybody already done a carbon footprint? You can go online, and like the EPA or the Sierra Club have places where you can do it all online. It says you don't even have to find your bills. It just kind of asks you some general questions. How many miles do you drive a week? And you type all these things in, and it'll give you a number. those are fine, but they're not very transparent. Something's happening in the background to do the calculation, and it spits this number out at you. And I'm not suggesting the number's wrong, but you don't know exactly what they're doing. With a simple spreadsheet, you can really calculate it. And so what normally happens in those sites is they take the average U.S. electricity, right? So their number is not as carbon intense as Virginia electricity. And so it's not going to be accurate for everybody.
All right. Well, if there aren't any questions, we thank Dr. McGinnis again for his time today. Thank you for coming.
And I'll hang out up here if you've got questions you want to answer. Thanks for coming.
Questions about tech, the Green Engineering Program.